Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by Ultra Air, whole house ventilating dehumidifiers. Here at Positive Energy, we've been working with these dehumidifiers for years on many of our integrated mechanical designs, and we've seen such great results for both the health and comfort of our clients. We even have an Ultra Air dehumidifier in our office, and we absolutely love it. When you're working with an airtight and well-insulated building, you quickly notice the outdoor air infiltration restrictions that occur, which allows pollutants and moisture levels to accumulate inside. So when you think about it, properly controlling that moisture in your home will definitely improve the effectiveness of your air sealing and insulation efforts, and will definitely improve the health and comfort for your client, your family, you. Just imagine being able to run your air conditioner at a higher temperature without feeling uncomfortable, and knowing that this improved comfort is coupled with fresh filtered air. These are just a few of the many benefits of incorporating the Ultra Air dehumidifiers into your home or your project. It really is an easy choice to make. To learn more about the best strategy for controlling moisture in your home, check out ultra-air.com, that's air with an E at the end, and see how a whole house ventilating dehumidifier can work for your home or project.
Welcome to the Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Okay, hello and welcome back, everybody. I'm Kristof with the Building Science Podcast. Very much appreciate you here listening. Today I have a real treat for you. I have a friend and an associate with me, a gentleman named John Semmelhack. He's with Think Little. He's a building science consultant in Charlottesville, Virginia. And John and I have the honor to get together often at conferences, and I think we've done a workshop or two together. We did a design charrette in Oklahoma a couple years ago too.
That was fun, except for the smoke.
Yeah, we were in a casino, and that was the less fun aspect of it. So, John, actually, since you've already spoken, please go ahead and introduce yourself a little bit to our audience. Maybe your background and what you're doing now, generally.
Oh, sure. So I started this company back in early 2008, just before the big recession, which for me turned out to be no big deal because interest in green building, energy efficiency, and building science has only been on a strong upswing before and since then. So we're a small two-person consulting company in Central Virginia in Charlottesville. We work with architects, home builders, multifamily developers, and homeowners and their clients to make better buildings. So buildings that are more comfortable, use less energy, and are more durable.
Excellent. Yeah, and that tempts me to go into the business of building science because to be a small but growing building science firm like you and I are, we're pretty much a pure building science play, right? We're not, like, that I know of, you don't have a government contract or a Department of Energy contract hidden away that's funding you somewhere.
No, not at all.
Yeah, so it's...
I mean, that would be fun. That would be an interesting side diversion, and I thought about that because we do like to get into our own little kind of self-funded research projects that we do.
Oh yeah.
We are always curious, and if we don't know something and can't find data on it from somebody else, we try to go out and measure it.
Yeah, I love it. Yeah, kind of grassroots building science and grassroots building science research. And there's not that many of us out here doing it, but there are several, so I'm glad to point out what we're doing. So for listeners, again, John's company is Think Little in Virginia, and we are going to start by thinking big today. The biggest thought I can think of is this, as a global society, as a race of beings living on the planet, you almost might say. I don't know if everyone listening is aware of this, but the global economy is shifting from being powered by fuels to powered by technology. And that the implications of that are huge. and we're going to watch them play out for the rest of our lives. And fuels, I would just want to be clear. I mean, back in early society, we burned wood. And then, for instance, all around London, the forests were wiped out. There was no more wood for building or fuels, so we started using coal. And of course, when society found out about oil, that's been a huge growth in the economy, actually quite literally fueled by oil. And today, we are transitioning to the clean energy economy where the goal is 100% renewable energy. Solar and wind are technologies. The fuel is the sun. I guess for wind, the fuel is the sun. Uneven heating of the earth. Yeah, uneven heating causes the mass of air to flow, trillions of tons, like a big river. So yeah, you and I are in that industry, John. You know, the grid is a machine to power buildings, and to the extent buildings need less power, transforming the grid is a more doable goal. What are your thoughts about transforming our grid?
Well, yeah, I think long term, or the shift is happening a lot faster than people realize, I think. But it's happening with the existing electrical grid, and then I guess it needs to, or it's starting to happen in transportation, where we're moving transportation to electricity based, mostly battery based. So we're adding vehicles to the grid essentially, and then at some point, more and more of our what I would call kind of low grade or low temperature thermal loads, like space heating and water heating and things like that, need to be moved onto the grid if we're going to power them with wind and solar. Or what I like to think of in terms of the big picture is we're moving from powering our world or our energy services. We're moving from powering them with really, really old solar energy to moving to current solar energy. So instead of using fossil fuels, which is still energy that basically came from the sun, it's just really old. We're powering it on current solar energy, wind, solar, and a little bit of biomass and some other things, but mostly solar. So the kind of the goal in terms of people who work in energy efficiency, or the need, is to kind of make room on the electrical grid for the other services that we need to electrify. So I feel like we need to electrify transportation and these low temperature thermal loads and move them onto the grid, ideally without increasing our total generation of electricity, because if we keep increasing generation, that's just going to slow down the transition to 100% renewable energy. That's right. And that's really interesting. Over the last 10 years, we've basically been flat on total kilowatt hours of electrical generation, while this is in the U.S., while adding millions of square feet of buildings and several 100,000 electric vehicles to the grid. So something is starting to work.
Exactly.
And I'm somewhat optimistic on the efficiency side. I'm very optimistic on the renewable energy production side. And we need a lot more work on efficiency, transportation, and then moving these low temperature thermal loads onto the grid. So if you're using natural gas or propane to heat your water or heat your house or your commercial building, in the next 50 years, that kind of needs to move to electricity.
Absolutely.
And it probably means heating with heat pumps, in my opinion.
It's our opinion, I guess I could say it that way. And I just want to be clear for listeners that when you're talking about low grade thermal energy demand, we just want to be very clear. We're talking about heating your water and heating your house, right? So when you heat water to shower, it's 120 degrees. That's a very low temperature, and your house maybe 70, 75 degrees. Again, a low temperature as compared to the 3,500 or so degrees that you get when you burn a gas molecule. Yeah, gas molecules are precious. They're rare. Well, they're not rare per se, but we're certainly not making them as fast as we're using them. And what we want to use them for are high temperature, high grade processes like manufacturing and materials processing. Possibly sending people to other planets, I guess.
Maybe.
But certainly not to heat water and heat air.
You know, in the big picture, long term, yeah, using those things that can create high temperatures to do things like melting metal, melting glass and rocks. Those kinds of things can't be done with people.
Exactly. So you can imagine a future us, future Americans or future people living on the planet saying, there's no more fuel to melt glass. We have this solution. We can't melt the metal and glass because previous generations heated water to 120 degrees with this fuel.
Right.
Yeah, so it's a bit of a Charlton Heston-like moment when it comes to the gas range, though. His quote about prying his gun from his cold, dead hand. I don't see people willing to cook on induction cooktops anywhere near the uptake of...
I've had such a good... I've had a really good track record with custom homes.
What is it you say? I get heat pump water heaters and I get heat pumps into houses.
I don't really say... I give them my spiel, but then I say, come over to my house and try it out because I have one.
I need one
at my house. Yeah, so it really... Because with an induction cooktop, you can't typically try that out at the appliance store. You can't actually cook on it.
So what is your spiel? Before you answer that, I tell you, I had a client just a few days ago basically tell me that being able to bend over and see how big the gas flame was a metric or an input that was used to cook. How do you get away from that?
I don't know. I've been cooking on my induction cooktop since 2008, late 2008. So we've had it for 8 years now, more than 8 years. And I love it. I grew up with gas. I've lived in places with gas cooktops, old school electric coil cooktops, and now induction. And I would go back to induction again and again and again if given the choice. Tell
me why.
Yeah. It's, I guess, the easiest thing to point out is that it's fast. It
delivers heat quickly, you mean?
Yes, so you can heat a pot of water or kettle more quickly than with gas or standard electric.
So the BTUs per hour is faster.
BTUs per hour delivered to the vessel is faster.
Yeah.
That's a key distinction. You might have significantly higher BTUs per hour with gas of the amount of energy that you're but that doesn't mean it's going into the pot. So you also have fine level of control. You can set your induction cooktop to a much lower heat input level than you can with any gas range that I've experienced. So you can have it on just barely warm. You can. So if you need to just keep something warm, or if you are cooking some kind of fancy sauce that needs to be at a very finely controlled temperature, you can do that with an induction cooktop. So you have the same level of, in my opinion, you probably have a more finely tuned level of control than you have with gas cooktops that I've experienced.
And so the feedback is the knob. You have, like, if you have a pot of water boiling, you can turn this knob up and down and just watch the bubbling respond right away. Is that correct?
Right. Or, I think with most induction cooktops, it's a touchpad. So
it's a touchpad. Tell me about that.
Well, it's more like dealing with a modern dishwasher or cell phone or something like that. Most of them are not dials.
Oh, interesting. So it's not even an analog control. So you press a button to go from level 1 to level 2 or something.
Right. Or I think mine goes from 1 to 10 with some half steps in between. On the lower end, there are smaller steps. And then as you get into the higher power levels, they are bigger steps. Because you don't need to go from typically a super boil to a medium boil in most cooking.
Okay.
Most of the time, boiling is boiling.
All right. Well, we certainly jumped a lot of levels there from
I do
low
tell
temperature
people
thermal loads to.
with induction cooktops, I do tell people, the downsides. There's some limitations in terms of the cookware. It does have to be iron based, so cast iron or steel. So there's that. If the power goes out and you don't have backup generator or backup battery, then you're not cooking on your induction stovetop, whereas with gas you can. And then the induction cooktops have a small computer basically living inside them, and if that control fails and needs to be replaced, it's a little bit expensive to do that. So that would be like a $500 replacement if it fails outside of warranty.
And cost for the overall cooktop?
Oh, they range from like just over $1,000 to probably over $3,000 for one of the high-end brands.
Excellent. Okay, so let's get back up and start working our way back down, because we kind of jumped from grid level, low and high grade thermal energy demand to induction cooktops. Kind of funny. But I want to get back to when you said you're optimistic on efficiency, but more optimistic on production. And on production, you mean we're talking about this by industry, for profit market transition that's occurring with wind and solar and regulation, although that might be shifting for the next few years.
Right. Yeah, I think there's just the rate of change on the renewable energy production side has been really, really fast. And I'm less optimistic on the efficiency side, especially with existing buildings, because of the economics. The reason why the renewable energy in terms of wind and solar is taking off so fast is because their costs have dropped so significantly over the past 10 years, and especially over the past 5 years, that they are now competing or outcompeting fossil fuels for new production. And we saw over 2/3 of new generation in the U.S. was wind and solar last year, which is the same as it was in 2015. So renewables are beating out fossil fuels. But in terms of existing buildings, it can be really expensive to take an existing building and dramatically alter it to reduce the heating and cooling energy use. And there's a lot of different levels of resistance to doing that. And so I'm less optimistic with especially with existing buildings. And side note, most of what we do is work on new buildings, because that's where the demand for our services is.
And the existing buildings paradigm, right? So if existing buildings are going to be harder to make them energy efficient in how they operate, that to me it just raises the stakes or increases the sense of urgency I have on my project teams to motivate them to really go with more efficiency. And
because new buildings have to be even better than
exactly. We got to make up for the. It's absolutely true. I mean,
you have to make up for the laggards in the existing buildings, I guess, or you're trying to. I like to think of having a building that almost acts like a ghost on the grid, like it's almost like it's not even there in terms of the big picture grid. I like that idea, something that just kind of floats in terms of its energy, because it's using so little and ideally is producing some or all of its energy needs on site.
Yeah, and I'm tempted to go back up and talk about the grid, but let's stay here. Because this is really the core of it. This is where the building science is, and this is the Building Science Podcast. So let's go through a building real quick, you and I, John, if we can. I think we're about 20 minutes in, so maybe another 20, 30 minutes. It should be easy to talk through everything from foundation to roof and all the systems inside a building, right? That should take 20, 30 minutes. So foundations. What kind of foundations are you seeing on your projects there in Virginia? And you do work in Pennsylvania as well. Other markets?
In Pennsylvania, it's mostly on the multifamily side for projects that are going for Passivhaus certification in the affordable housing low-income tax credit program up there. Those projects are almost entirely slab on grade. That's pretty standard for that kind of building type. In Virginia, with the most of our work is in single-family homes, detached and attached townhouses. Those are mostly basements and crawl spaces with a little bit of slab construction. Sometimes slab on grade, sometimes it's like a walkout basement. So you have a half slab on grade.
Mm-hmm. And when it comes to the decision on the slabs, or if it's a half slab, when it comes to the decision on whether it's cost effective to do slab edge insulation, how do you approach that, or is it simply a code requirement you follow?
Well, we have a code requirement, so we have a minimum R10 at the slab edge, either going from the top of the slab going down 2 feet, or protecting the slab edge and then turning underneath the slab and coming in for 2 feet. So that's the minimum. It always is a little tricky to figure out the detail of how you handle the foam. Is the foam going in between a stem wall and a poured slab, or is the foam going vertically on the outside of the stem wall, going down to the footer? And if you do the latter, how do you protect the slab insulation that is exposed above grade? And so different permutations for different kinds of projects.
And termite tubes factor into that as well?
They do, and thinking about how you protect the wood insulation the wood, typical wood framing that is above grade in terms of that transition. Termites are an issue in Virginia. I imagine they're not nearly as bad here as they are in Austin. In terms of my particular experience, I haven't seen. It seems like our termites, at least locally, are relatively lazy. If stuff isn't wet, they don't go for it. So it's going up. They'll eat right through anything that's wet, but as soon as they get to dry wood, they stop. So if you keep your wood dry, it seems like you're relatively safe here.
Yeah.
So
we actually have carpenter ants that fly here, so it can be a real challenge. So you brought up Passivhaus, and that's something I'm bonking myself in the forehead for not having brought up early on in our introduction here. So that's one of the main ways we know each other. We're both PHIUS devotees, if that's...
That is, yeah. That's how we met. You were our original ResNet liaison.
Yeah, that's right. Yeah.
Back in the day. So that's how we first met.
Several years ago.
I've been I guess as far as the United States goes, an early Passivhaus devotee.
Mm-hmm. And you live in one, correct?
Not quite. No, we live in one. We did.
Confessions?
No, yeah, it's. I'm not going around telling people I live in a Passivhaus, but we did design the house as close as we could at the time. But, when we designed the house, I was an amateur building scientist, amateur energy modeler. So I learned as much as I could at the time, and we got pretty close to the standard, but not quite there. But the house is still lovely, and we recently made a couple of improvements to it that have been really great.
Your EUI, do you happen to know that number, or your energy bill, or some quantitative way to assess how it's running, how it's performing?
Oh, let's see. Well,
You don't have to eat.
Sorry.
Tell me, how much did you pay for electricity last year? It's all electric, correct?
It is all electric. It's a little convoluted now because we added on a mother-in-law apartment last year. But for our side, our EUI is just over 4.
Awesome.
If you don't count our solar production. So with our solar production, we are net positive for our side of the house. If you include the mother-in-law apartment, then we produce about 80% of our energy on a net annual basis.
That is awesome. So just for people listening, just to put that in perspective, right? So EUI is the energy use intensity, and it's simply the energy in BTUs or kilowatt hours, but typically you were doing BTUs.
No, sorry, I was doing kilowatt hours.
Oh, so it sounded a little better. So you're really more like 12. Is that right?
12 kBTUs per square foot. Yeah.
Mm-hmm.
Mm-hmm.
Yeah, and so the average in the U.S., instead of being, John's at 12, the average in the U.S. is typically in the 40 to 50 range. And Architecture 2030, Ed Mazria has a challenge that, takes us from that EUI down to target EUIs, and they go as low as 4. John, you're at the level of like the 80% targets, the 70 to 80% target.
Right, which, realistically is, it's about as low as you can go through efficiency. And then at that point, there's only so much more you can squeeze out. You can't squeeze much more out of your cooktop or your, I guess we could improve our clothes dryer or our refrigerator. There's not much better that we can do. So at some point you just have to switch over to producing energy. And that, the economics of that has changed a lot.
Oh, absolutely.
And so that we're always revisiting that conversation with new clients, making sure we're on top of that. And I personally have a bias towards reducing energy use rather than producing energy on site. But you have to, meet your clients where you are in terms of that conversation and deal with the reality of their budgets and their plans.
And just to expand on the EUI and the Architecture 2030, my understanding is the Architecture 2030 would allow you to factor in on-site power production.
Oh, yes, absolutely. Yeah.
And so you are actually, their 100% targets are trying to get to 0, and you're there. So you've made it. Now, when I mentioned that the average EUIs are in the 40 to 50 right now for single-family, multifamily homes, that's just on site. Those numbers go up by a factor of 2 to 3, depending on the gas versus electricity mix,
right.
If you go to source energy. So yeah, we've got a long way to go. I mean, if buildings on average, and by the way, when the projects we work on, newer projects, we're getting the, down as low as in BTUs, kilo BTUs per square foot per year. A good one would probably be 15, and a lot of them are close to 30. And that's with a lot of efficient equipment. They're just larger homes, but they are early adopters in some sense. They're making it more common for high efficiency equipment to be used. But
right.
back to PHIUS in Pennsylvania in particular, this low income housing tax credit. Tell me a little bit about that. How is that changing the market for low income housing design, I guess, or not just design, construction?
Well, that's so in Pennsylvania, the PHFA, the Pennsylvania Housing Finance Authority, they manage the low-income housing tax credit awards that go out to development groups every year. Most of that project financing is competitive. So potential projects submit their applications each year, and the way each state has their own program and they manage it slightly differently. There's a lot of similarities, but many states award or offer optional points that developers can check off these boxes. So if they pledge to keep the rents even lower than certain levels, if they pledge to make these apartments affordable to more of the population, they make their project more competitive on the application. And these finance authorities realize that if the tenants, who mostly pay the energy bills, if they're paying less money for energy costs, that helps their finances quite a bit. So they have incentivized energy efficient construction on these applications. So in Pennsylvania, they added a checkbox for Passivhaus. And they also added a checkbox for exceeding Energy Star, and they put them at different levels. So you can make your project more competitive by checking the Energy Star box, or even more competitive by checking the Passivhaus box. So many of the developers are opting to check that Passivhaus box, and some of those projects are getting the financing award. So roughly the past 2 years, about a quarter of the projects that were awarded funding had checked the Passivhaus box, and I've been lucky enough to be a part of the project teams on 4 of those. One is under construction in Pittsburgh, and 3 more are just wrapping up their financing packages and are pre-certification with PHIUS, and will be under construction late this spring.
Oh, that's so great. I mean, how that PHFA included PHIUS would be an exciting story to cover for a different day.
It would, and it's really, so Tim McDonald in Philadelphia, who's an architect and part of Onion Flats develop, design, build team in Philadelphia, he's really been the key person who got this implemented in Pennsylvania, who really pushed for it, and he's been trying to spread the word all across the country. And so we have other states now who are putting Passivhaus on their applications, and we're starting to see other places where it's starting to take hold. So we'll see how it goes over the next several years. I think it's really it's obviously really critical that these early buildings that we have a good experience for the developers, for PHFA, for the actual energy use and so on. So that's something that we're really interested in on our projects.
Mm-hmm. And as we know from the conferences, I mean, generally the story is that it is a positive experience, that the cost add goes down each project because the teams get more familiar with it. And what we can't forget is that embedded in this energy paradigm is improved health and comfort as well as building durability. I mean, a Passivhaus, a high-performing building, is not just one-dimensionally better. It's generally better. It's a generally
right. Yeah, we're certainly trying to, on every project, we're trying to positively influence comfort, energy use, health, durability. Those kind of the 4 key things that we are really looking at on each project.
All right, well, let's get back now. We got to accelerate even more. Let's get back to building our let's say it's a single-family home. So we've got the foundation in. Let's, for simplicity, just say it's a slab on grade. Slab edge insulation, you're putting that in because it's code. You're also running a model, correct? Typically, or how does that work for you?
It depends. So one of the interesting things, in my opinion, with modeling is that the more energy modeling you do for particular types of projects in a particular place, the less you need it.
I get it. I agree.
When you start to settle in on a package of building enclosure types, or you have a kind of a palette of building assemblies that are going to work, that are kind of optimized for your climate, for efficiency and economics, are buildable by your local builders, and so on. So we don't always do whole house energy models. Many of our projects we do the mechanical system design, so we are going to do a heating and cooling load calculation model, but we might not do a whole house energy model, really, unless...
Yeah, I get it.
Yeah.
Modeling definitely has its place. I mean, highly custom projects, owners with really clear goals as far as energy independence, and if you have very tight constraints on PV production and you want to go net zero, I mean, there are times where modeling makes sense, but I agree with you. Generally speaking, you can also approach it from somewhat what the model will say, and you also know where the sweet spot is as far as what the local installer community and supplier community has for you to build with, right? It's something
exactly. Yeah. And so we, not only have those kind of, I guess you might say prescriptive solutions for the building enclosure, but we're at that kind of point with mechanical systems. We can look at a plan and a given building enclosure and window spec and door spec and say with pretty good accuracy, oh, that's going to be, 2 slim ducted heat pumps, and they'll either be 3/4 ton each or they'll be 1 ton each. And we'll do one ERV, like 100 CFM ERV. And that's probably what we're going to do on this project. We'll double check with our load calculations and our ventilation calculations, but we can get a pretty good idea in just a few minutes of what generally the mechanical system is going to look like.
Yeah, and we're the same way. We can generally outline the components we'll need, but I think let's not overlook how important it is to run loads and to do proper design on the air distribution system, and to pick the diffusers carefully and locate them carefully.
Right. The selecting the equipment. I guess doing the load calculation and selecting the equipment is the easier part of the HVAC design puzzle.
Correct. It's integrating it into the framing and into the space and the architectural design.
Exactly. Yeah. And with our preferred heat pump systems, we have limited fan power that we're working with, so we have to keep the ductwork quite smooth. We have to keep the pressure drop from our filters and fittings and things like that quite low, while at the same time, having enough throw out of our registers, so we're getting good mixing within the rooms. So it's it definitely it takes work to get from point A to point D, I guess.
Yeah, I think that's like a hidden feature in mechanical system design. Let's say you've got a client and they've said, okay, I want to do VRF, and I understand that these variable capacity systems give me efficient part load. But it doesn't end there. What you were just alluding to, if we're using these low static pressure units, that means much more precision and care goes into air distribution. But a lot of times what people say is, oh, but a high static air handler, is available for that system, so let's just do that. Well, suddenly you've got, less stress on but you've got more energy use.
Right, yeah, you're throwing away all of that energy just because you've decided that you don't want to think about the problem and work through a solution. That's my opinion on it. It seems to do you do a good duct layout and specification and register selection and filter selection, and you can drive your fan power down to 1/10 of a watt per CFM. I don't know if you look at it in that metric, but
yeah, I do.
That's kind of my goal. Obviously, it takes a very efficient fan motor to begin with, and then a good duct design.
But it can go up almost an order of magnitude from there if you're not careful.
Yeah.
And I could tell you just an anecdotal story. Austin market, 2008, 2009, I really got into these low static heads. I wanted to use them. And to my credit, not to my credit, to my installer's credit, I was able to find some that would trust the fact that I could do a distribution design and I could show them that it would work. But many installers would say, no, we're not using those. They're the low static units. We refuse to use them because we consider it threatening to our business model.
Yeah, and that's where our focus on testing stuff that we design. That's one of the things that we do. Any mechanical system that we design, we insist on doing the commissioning work. So we set the speed settings on the air handler, and we balance the system once the building is finished. And we won't do a design where we don't do that. And so that means that we get to see what works. And we have real-world proof and numbers that we can show to installers. And we can say, hey, we've got these, dozens of, low static pressure air handlers moving the right amount, the amount of air that we said it was going to at the static pressure that we set, within a, certain amount of tolerance of what we said it was going to do. And so now we have proof. And that's one of the great things about actually measuring stuff.
Absolutely. Engineering and physics works, and never discount the value of testing your own work. So let's trying to go through several things here. Ventilation. How are you doing ventilation? You mentioned ERVs, separate ducting, piggybacking on the heating and cooling ducting. How are you doing ventilation?
So our preference is ERVs for ventilation. We typically get rid of the bath fans, do continuous exhaust from the bathroom, sometimes a little bit of exhaust from the kitchen as well. So the exhaust side is all its own independent ductwork. Then on the ERV supply side, our preference is to do standalone ductwork for supply ventilation, but it does add a little bit of cost to do that. So in some cases, we will duct that in to the ducted heat pump system or systems. Often, if we have two slim duct heat pumps, we'll split the ERV supply air and send it, 50-50 or so into the two heat pumps. With the air handlers that we're typically specifying, those run 24/7. So even if the compressor's not running, they will run at a very low speed and low fan power, which is great because then we know that the ERV supply air is moving downstream, down the supply ductwork and out the registers, rather than short-circuiting and coming out the return grill.
Return, yeah. Yeah, and it's also great because it's filtering and mixing.
Exactly, yeah. So we, the systems that we use in that, in the low, super low power mode, it's about 10 watts to move the air, to keep that air handler moving, which is about the same amount of power input that most heat pump systems require just in standby mode.
Yeah.
So I don't mind that 10 watts at all. We get constant filtration through the Merv 13 filters that we normally specify.
What about dehumidification? I guess it depends on the climate zone. Tell me where your thoughts are on that.
So we're in climate zone 4, so we're mixed humid. So we definitely have humid summers, and we have swing seasons. We typically get a week or two in the spring and a week or two in the fall where it's 70 to 75 degrees outside, so there's very little sensible cooling load. Mm-hmm. But it's just wet outside. It's either raining or it just rained or it's just about to rain. And for the most part, we leave that up to the individual clients what they want to do. We can, in our climate, with just our variable speed heat pump systems, we can handle our moisture load 95% of the time and keep our relative humidity under 55% on those projects, except for those 7 to 10 days in the swing seasons. if the client wants perfect control of the relative humidity indoors, 365 days a year, then we would specify a ducted dehumidifier. One other thing that we do look at is obviously the sensible to latent cooling load ratio for the particular house. And through experience, we've seen a couple of houses where they've had so much tree cover, for instance, on top of quite low solar heat gain coefficients on the window glazing, that the sensible loads were extremely low. And that kind of extends the number of days each year where there's just effectively zero or near zero sensible cooling load, and those are the kinds of houses where we really need a supplemental dehumidification system.
Right. Yeah, and so that's sort of my overarching consideration with dehumidification. First of all, it's a huge health-related impact. But second of all, as we continue as a society to make buildings more energy efficient, what that really means, that's a euphemism to say require less heating and cooling. And when you require less cooling, you require drying still for health.
Yeah, that's one of the interesting things that I like to talk about with people, and I do some teaching for PHIUS in their certified Passivhaus consultant training program, and I definitely think that there's a limit to how low we should be driving the solar heat gain coefficient on our windows, and I think there's a limit to the amount of shading that we should be doing on some of these projects unless we have supplemental dehumidification.
Yeah, and exactly. The outdoor conditions, for instance, in winter, it's free heating, right? And you want to be careful not to constrain
Exactly. Yeah.
Let's try to keep going through filtration when you're managing static and keeping these systems at very low static pressures, so very low energy moving through across your filter too. What kind of Merv ratings are you able to get?
Yeah, this is one of my favorite topics to talk about over the past couple of years. So we're pretty much using Merv 13 filters across the board. We are almost always using filter grills, and the
2-inch?
2-inch deep filter grills. A couple of reasons for doing that. Number one is that we can filter it before any air moves into the ductwork. So as long as our contractors do a good job of keeping the ducts clean during construction, we can keep the ducts very clean after construction. So that's nice. And then second is it's a lot easier to control the surface area of that filter at the filter grill rather than in the duct. So it's easier to do it kind of out at the wall or the ceiling. And that is where we size the filter grills to keep the pressure drop from that Merv 13 filter to a very low level, where it's almost non-existent in terms of the system.
That's exciting. So you're able to do Merv 13 with the 0.1 watt per CFM.
Absolutely, yeah. So right. On a 1-ton ducted slim ducted heat pump, we would normally spec a 20 by 20 by 2-inch deep filter grill and Merv 13 filter. And the other great thing is that it's really cheap to do that. The 2-inch filter grill costs about $30 wholesale. The filters themselves cost about $10 or $11 each when you buy a case at a time. So you can get this installed you can get a Merv 13 filter with extremely low pressure drop installed for about $50.
That's exciting.
With my design, instead of $400 or $500 for a Merv 13 4-inch media filter with a very high pressure drop with kind of a standard package system from the big guys.
Yeah, that's a big moment. That's an exciting moment. Let's keep moving though. So testing, I actually don't want to bog down there. I want to go to 2 different places. But testing, I want to tell remind everyone, right, that so much work on a house, on a project, multifamily, commercial, anything, goes into the design. And that's like working on the recipe for a meal. You really want to taste the food too, right? So you really want to measure your systems. And, you know, so that's one aspect of it. You want to, like, your client doesn't actually live in the design. They live in the house that got built. So you want to measure exactly those airflows and the temperatures and humidities that are coming out in cooling mode and things like that. But for companies like Think Little and Positive Energy, for us to have the opportunity to do design and testing of our own designs, it's a huge positive feedback loop. And I think it's one aspect of our industry which is a bit segmented, where it would be better if it were more integrated. If everyone tested their own designs, I think it would be better. Any quick comments there? Because I have two more topics.
I really agree. I think, you know, the few you know, people that I know in our industry who design some really fantastic mechanical systems and install them and test them, they are you know, they're probably the best people out there.
Mm-hmm.
You know, it would be great if that is what everybody did. If every installer took that amount of care into the design, the installation, and then making sure that the system is actually working right in the end. So that's kind of the gold standard, I think, and that would kind of, you know, sense that would put me out of business.
Yeah.
Maybe I would wind up going to work for them. But in the absence of that, you know, we get to at least work on the design side, and then the tail end, the you know, testing, balancing side, and work closely with the installers to make sure that the installations are up to our standards.
Yeah. And I could see a lot of the faces of the people you're talking about, like the Henry Gifford, Mark Rosenbaum, Gavin and Dan.
Yeah,
these
Mike
are the guys that are. It's amazing how much research they do in addition to running a business. So I have, you know, I was going to talk about lighting, but let's skip lighting. We just talked about last episode. So I have two different CAs. One is controls and automation, and the other one is construction administration. And I think after that, we're at our limit here, John. So with regard to controls and automation, what are your thoughts on that? And I guess particularly how it affects energy efficiency.
So, yeah, that's an interesting topic, and I'm open to new ideas about this, but my current bias is to lower tech controls. With heat pump systems, with my heat pump at home, my ERV at home, I set it in the winter and then I leave it alone the entire winter. The ERV runs at the same speed all the time, and I do nothing to it.
Summer and winter for the ERV.
Summer and winter. ERV runs the same. I change the temperature setting, you know, for the heat pump. I will switch it over to cooling mode in May, or, you know, maybe earlier this year because the weather's been so crazy. But I'll switch it over to cooling mode and adjust the temperature, and then I'll leave it alone. I don't. With the kinds of systems that we use, they seem to, from a comfort standpoint and energy efficiency standpoint, they do better with a kind of set it and forget it mindset. And so there's no big benefit to setbacks or smartphone controls or things like that.
Right. Yeah, it's interesting because just to do a quick plug, you know, we both listen to the Energy Gang, and we know that intelligent efficiency or electronic efficiency it's a big topic, right? And certainly for commercial buildings and manufacturing, it has the potential to save a lot of energy just by knowing when you should run that appliance, or in the home, when you should run your dishwasher, when you should run the washing machine for your clothes.
Yeah, so you mean like in terms of shifting,
load shifting, exactly.
Moving out the curve of the grid peaks.
Right. So it's almost like what I was getting at is that the controls and automation piece, it bifurcates, and there's like the ergonomics of controls, like how do you and your family interact with your control systems. And then there's this invisible controls layer that can occur in the background. Like you say to your dishwasher, start, and it knows that, okay, what he really means is by tomorrow morning, he wants clean dishes in here.
Yeah.
And I don't need to start right now. I'm going to wait until the signal from my power company switches to a lower tier, which is, it's all part of this evolving paradigm, the clean energy economy. So I wholeheartedly support that, and yet I'm with you on simple is typically better, and that's, I'm sure, most of us based on experience.
There are some loads in the house where that's going to be a bigger thing. Like your dishwasher load, is the benefit of the grid going to be large enough?
Dryer, maybe.
Or in a low load house, my peak power input to my heat pump in my house is about 1,000 watts. And that's not much in terms of the grid. So if we shift that from one time to another, it's not helping all that much. Mm-hmm. So I'm a little skeptical of the kind of cost benefit of doing that for certain loads. Now,
and for certain types of buildings, is that really what?
I think there are other building types and other pieces of equipment where there can be huge returns on doing that. And so I think in low load houses, the biggest thing that we have done in terms of helping the future grid manage peaks is just by reducing the loads so significantly. And once we have reduced the loads by 75%, 80%, shifting the tiny bit that's left, I don't know if there's going to be that big of a return. Shifting an existing house's loads, that's probably going to be a much bigger return.
Yeah. All right. So the last CA, and then we'll wrap it up here, is construction administration and personally and professionally integrated project delivery. This idea that building science consultants, mechanical consultants like you and I, obviously people value our input up front. But what I'm finding is that it's so important that our input remains on the project after design, through construction, and through final testing. So it's not like we hand them our design and say, good luck with that. You are doing support of construction, is that correct?
Yeah, so like I said before, especially with the mechanical systems, we will not do a mechanical system design unless we get to inspect it and test it. So we're looking at the ductwork at rough-in, making sure that it is installed the way we drew it, with a certain amount of tolerance for transferring something from the page or the screen to 3 dimensions. But and we're doing a preliminary duct leakage test so that if there are leaks that need to be fixed, they can do it before drywall is installed. So it really I think it really is important to have that, to have somebody on the project whose responsibility it is to get all these things done, and for certain details to be really watching over those.
Absolutely.
Because the general contractor has literally a million other things to worry about. Mm-hmm. And they don't necessarily have the expertise or the time and attention to be able to look at the things that we look at.
Yes, I agree completely. I mean, right there where you just mentioned that the project managers, the GCs, really smart, hardworking people, and yet when they look at, for instance, air distribution system, a supply plenum, they're probably not they could be looking at one that you and I'd walk in and go, whoa, what the heck happened here, right? But it would look like, they wouldn't know what to cue in on. And so we can train them over time, but right now I know, and another thing, I'm on a job site and I'm there to look at our ductwork, and I'll see something on the control layer side, or I'll see something, completely separate from my scope of work. that it's like you really need to pay attention to that right now, right? You've got your rain pants tucked into your rain boots there. And it's going to do
Yeah,
something.
we see that every now and then, especially on multifamily projects where we're inspecting insulation, or we're doing a preliminary duct leakage test, or any number of different things, and then we see a little bit of water where there's not supposed to be any water. And we go investigate, and we try to figure out, where's that water coming from? What flashing failure is going on right now? How bad is it? How long has it been going on? What needs to be done to fix it? And then we go talk to the site supervisor and project manager, and make sure they understand what's going on. So it's often we're the ones who wind up catching those things.
Mm-hmm. Yeah, it's interesting. I've told clients that it seems like rain during construction is a bad thing, but we really need to rescope and think it's actually a good thing. It pointed out a weakness that once the house was done could have been
That's
much
true.
bigger.
Yeah, especially with really severe sideways rain.
Yeah. All right. Well, so any final thoughts? Any final comments?
Oh goodness, we didn't even get to talk about heat pump water heating. We'll have to.
Oh, dude, let's talk about that for 3 minutes. I actually have a meeting coming up I need to go to.
We have to move the water heating, and we have to move that load onto the grid, right? We kind of talked
Absolutely.
about that. That's my premise. Eventually, all of that water heating has to move onto the grid.
And so it should be integrated with your heat pump generally, your air conditioner and heater.
Maybe, yeah.
Oh, come on.
There's pros and cons to doing that, but yeah, that would be